Okay, so I wanted to start today by talking about a notation that we're going to use for something like this that is going to be handy. So the same example that I keep talking about, here we have a simplicial complex. We make this the Stanley-Reasoner ideal, I sub delta. We make the Stanley-Reasoner ring, R mod I sub delta. And then we take the minimal free resolution, which is this one right here. And I computed it ahead of time, right? So this is what it looks like. Now, in the way that I'm doing it here, this is not really a graded free resolution because you're seeing that, for example, things of degree 1 here get mapped, things of degree 0 here get mapped to things of degree 1 here because you're multiplying by actual variables. And so we need to do these degree shifts, right? And so we're going to use a notation that will help us keep track of this stuff by doing this. So for example, I'm going to look at this part of the picture, and I'm going to redraw it for you like this. The thing is that, remember that the way that we got the grading for these guys was basically just by seeing what the grading had to be given the matrix. And for example, we know Can someone close that door? Thank you. So the point is this, that if we look at the graded Fourier solution, then by the fact that it's graded, it should take things of the same degree here to things of the same degree here. And so we want to write it in terms of a matrix that preserves degree, right? And then so what I did here is basically take out all the letters and keep the numbers, and the letters we're going to build into the grading, which is what we do. So the thing is this, for example, let's talk about what grading we need to put here on this r to the fourth. Well, here I have the normal grading, okay? So for example, where does the 1 in the first coordinate go? Here. So remember, an element of r to the 4 has 4 entries. So where does 1, 0, 0, 0 go to? It goes to DE, right? And so I need to fix the degree by shifting the grading over by DE on the first coordinate. And so I'm going to denote that by saying that the first coordinate gets degree shift 0, 0, 0, 1, 1, which corresponds to DE. And I'm also going to write that here, DE. The second coordinate here, the grading needs to be shifted by ABE. So I put that here as ABE, and I put that here as 1, 1, 0, 0, 1. Then this one by ACE, so I put 1, 0, 1, 0, 1. And this one by ABCD. And so I put 1, 1, 1, 1, 0. Okay? And the point is that by virtue of the way this goes, we're actually forced, the degrees of this guy force the degrees of this guy. So for example, we saw that what degree do we need to give to the first coordinate here? Well, the first coordinate here, if we put the 1 in the first coordinate here, we get a C in the second coordinate and a B in the third coordinate here. Now, the second coordinate is shifted by ABE, and so the degree is going to be ABCE. And the third degree has shift of ACE, and we're multiplying by B, So in the end, we get degree A, B, C, E. And that's going to force that the first coordinate here gets shifted by A, B, C, E, and we write that here. Okay. And we do that for all the other ones. And again, it's important that you stare at this table long enough that you see how to compute this. I can kind of point to it, but really you just have to stare at it long enough that you see it all work. But so this is what this piece of the picture looks like, and then it continues over here, and it continues over here. Okay. So all I did is kind of take the letters out, put them into the grading, and then now my matrices are just going to be scalar matrices. They look like this. Okay. This is called a monomial matrix. Okay. And given this monomial matrix, for example, you can read off the Betti numbers very easily. I mean, given this representation, the Betti numbers are very easy because, for example, what are the Betti numbers? Well, these are the Betti numbers 0, the Betti numbers 1, Betti numbers 2, Betti numbers 3. So for example, I said 0, 1. So what are the first Betti numbers? Well, they're exactly given by the things that appear here. For example, what this means is that, remember, this is F0, this is F1. So F1 is going to be R shifted by minus 0, 0, 0, 1, 1. Plus R shifted by minus 1, 1, 0, 0, 1, plus, etc. And that means that this tells me that the Betti number 1 in degree 0, 0, 0, 1, 1 is equal to 1. This tells me that the Betti number 1 in degree 1, 1, 0, 0, 1 is equal to 1. And then the other guys are also equal to 1. And then the Betti number of 1, comma, everything else is 0 because it doesn't appear in the first level. Okay. I think some of you guys were a little bit confused about what these Betti numbers mean, and so I wanted to say it again. It's basically telling you in the first entry of the resolution, what are the degrees that appear here, and how many times do they appear. In this case, it happens that things only appear 0 or 1 times, and that's why the Betti numbers are 0 or 1. But in general, you might have 2 copies of the same degree here, and then that would make the Betti number bigger. Yeah? So that's what the Betti numbers are. And remember that our goal now is to compute those Betti numbers. So this monomial matrix will help. Okay, so we were doing a little bit of homological algebra last time. And I stated but didn't prove this theorem that the Betti numbers of the ideal are given by dimensions of these Tor spaces. There's a lot of symbols in there, so let's... I think the best way to see what this statement means is to prove it, and then we'll see what all of these symbols mean. So first of all, remember what this Tor is. So to compute Tor of Fm, remember what we do is that we take a free resolution of M and we tensor it by F. take a free resolution of M. And so I'm going to call it like this. Okay. Let's call it maybe F dot. And then we're going to tensor this. We're going to tensor everything by M. Right? So what we get is something called F dot tensor M, and it looks like this. Sorry, we need the torr of F and M. So we take a free resolution of M, and we tensor it by F. So this is F right here. That means that this is F. This is F. This is F. Okay. And basically, remember when I defined this, I put an R underneath each one of these tensor numbers. But since R is going to be the same throughout, let me just simplify the notation a little bit and just you understand that there's supposed to be an R under each one of these things. Okay, so remember that what this does is that it says, okay, well, this sequence was exact. Now by tensoring by F, maybe we made it not exact, and we need to find out how inexact it is. And the homology measures that. Homology is the kernel of a map mod the image of the previous map. So that's what we're going to do. So we want the homology of this. So let's understand what this is. Okay. First of all, let's understand what happens to each one of these each one of these guys when we tensor it by F. So what's Fi? Well, by definition, Fi is a sum of copies of our ring, a direct sum of copies of our ring, and each copy is shifted by some vector A, and the number of times that this occurs is the Betti number, right? So I consider all possible shifts. And then for each shift, I say how many times it appears in my module Fi. Okay? So again, you should think about this, that most of these Betti numbers are equal to 0. There's only a few of them that are not equal to 0. Like in the example over there, we had exactly 4 that were not equal to 0, and they were all equal to 1. Okay, so, for example, if you put I equals 1, then you should be looking at that equation over there as what this is. Okay? Okay, so if Fi is this, then we have this. What is Fi tensor F? Well, there's one thing that is, we're taking a sum and we're tensoring by F. And it's pretty easy to see that you can either first take the sum and tensor by F, or you can tensor each one of the guys by F and then sum all of those guys. It's a nice exercise if you want to think about it. So I can just take each one of these guys and tensor them by F. Okay? And I do this beta I 8 times. Okay? So we just distribute the tensor across the direct sum. But the good thing about this is that we discussed last time what this is. We said that if you tensor any module by the ring, then what we get is just the module itself. And if the ring happens to be shifted, then the module inherits the shifting. So we actually made this computation explicitly last time, and we saw that the result of this is exactly the field shifted by A. Okay? And then this is to the beta I. Okay. So this is what these guys look like. Okay. Remember, we're trying to compute the homology of this guy, and now we know that the ith term is just a bunch of copies of our field, and they have some shifts. Okay. So this is these are the entries of the sequence, but now we need to find the maps also so that we can compute kernels and images, right? And so let's figure out what the maps are. So we have a map that goes from this guy to this guy. Okay. And this map, remember, is just the tensoring the, like I didn't give names for these things. But if I call the maps delta n up to 0, then these are just the, this is just the map delta I tensored with the identity. Okay. And so we need to figure out what this map does. Okay. What does this map do to something like this? I mean, maybe I'll just say it in words. The thing is this, that like we said, each one of these things is a bunch of copies of the field. Okay. So here we have the field a bunch of times, the field a bunch of times, and so we have some maps from the field to the field. Okay. But also, if you look at the way that our maps look, our maps never go to the same real degree. So each one of these guys is going to be 0, actually. One way of putting this is that you're never gonna see the same. I mean, in this case, we don't have the same degrees here and here. Okay. And if we did, I don't know, if we had, for example, DE mapping to DE, then it's actually easy to see that what happens is that this is not a minimal resolution. Okay. So let me say this explicitly over here. We have these things labeled by AI here, BJ here, and we have some number here. And it's kind of an easy check that what we have here is a free resolution. Sorry, this free resolution is minimal if whenever you have AI equals bj, then you put a 0 here. So I don't know if I call this, in my notes I called it lambda ji. Lambda ji should be 0 whenever AI is equal to bj. Okay? So what I'm saying is basically, if you have the same degree here and here, then your map should be 0. This is something that you check. It's not trivial, but you can check it. And so what I'm saying here is that you have a bunch of copies of the field here. You have a bunch of copies of the field here. They're shifted by a certain they shifted by certain vectors like this. But if you have the same vector shift here and here, then you're supposed to be the 0 map. Okay? And because these maps are degree preserving, then this is going to be the 0 map. So the point of me saying all of this is that basically, when you take this free resolution and you tensor it by f, then you're just going to get a bunch of copies of the field with certain shifts, and the maps are all 0, which means that it makes it very easy to compute kernels on images because these are just 0 maps. Okay? So what is Tor I? What's this? Basically, I just need to take the homology of this thing, right? Sorry, I should have said this was all for a fixed degree. Forgot to say that. We're looking at what happens in degree B. And what I was saying is that the map should be 0 when you map degree B here to degree B here, which is what this Tor is measuring. Because if you have degree B here and you have degree B here, then you're supposed to put a 0 map there. Okay? So that means that this guy is the homology of the degree B part. Okay? But what's homology? Homology is kernel of this map mod image of the previous map. Okay? But when you have a 0 map, then the kernel is just everything. Okay? And the image is coming from here, but this is the 0 map, so the image is just 0. Okay? And so all you get is fi tensor f in degree B. Okay? Now what's fi tensor f in degree B? Well, fi tensor f looks like this. And what are the things that live in degree B? Well, they're exactly the term here when you get B instead of A, right? So this is just f to the beta I comma B. And this is exactly the statement that I wanted to make. That beta, the Betti number, is exactly the dimension of this Tor. Okay. One thing that I should say that is kind of lurking throughout all this argument is that, what I have here is an exact sequence, right? Sorry, it's not an exact sequence, but it's a sequence. And the sequence is graded, right? And that means that if I consider this sequence, then I can now consider only the part that lives in degree B. And then I'm going to get some other, and because this is a degree preserving map, this goes from degree B to degree B. Okay? And it's in degree B that I perform this computation. So that's the proof that you can characterize these Betti numbers in terms of these Tor functor. So this is the first thing that I wanted to do. So this is the first step towards getting a handle on our Betti numbers, is we express them like this. Okay? But now what I'm going to do, my next step is the following. I'm going to say, I stated last time that Tor is symmetric, right? So Tor of m and n is the same as Tor of n and m. So here I'm giving you a way of computing the Betti numbers by saying, do this computation with Tor by taking a free resolution of m and tensoring by f. But Tor has the property that I can do that in the opposite way, by first taking a free resolution of f and tensoring that by m. And so I'm going to do that. And when I do that, I'm going to prove this very nice theorem that I stated for you also. Let's actually do it over here. So this is the first part of the theorem, and the second part of the theorem is that this Betti number is just a certain homology. Right? So this is something that I stated for you that I think you're probably already using in your homework. And it tells you that if you want to compute a Betti number, then what you can do is build this simplicial complex and compute its homology. So remember that K B of I is the upper Koszul complex of I in degree B. And that's defined to be the square free tau such that x to the b minus tau is beta. Oh, yeah, thank you. Because this is yeah. Yeah, so I guess the thing is this, that this statement right here holds for any graded module. And I think that's why I switched the letter to M. But this one is for monomial ideals. So maybe let's just use I throughout. Because this is the one that we're after, actually. We want to say if I is a monomial ideal. Well, let me let's keep these separate. So this is for a graded module M. And that's the proof. And this is for a monomial ideal this is what I'm going to prove. You can compute this Betti number by this homology. And the way I'm going to do it is, like I just said, I'm going to compute this in a different way by taking a free resolution of F which I'm going to call K, and then tensoring that guy by M. Okay. And I'm using that here. I have an isomorphism between Tor Fm and Tor NF. If you think about this, I don't know, some of you are in a Combinatorics class right now, and probably you've learned about this idea of taking the same set and counting it in two ways. And if you take a set, you count it in one way and you get an answer. You count it in a different way and you get a different answer. And that gives you a proof that these two answers are the same. So if you look at this, it's basically the same thing. We're looking at this Tor, and we're computing it in two ways. So if I compute it in the first way, I get this Betti number. And now if I compute it in the second way, I'm going to get this right here. So I'm supposed to take a free resolution of F and tensor it by N. So now let me ask you, do we know how to take a free resolution of the field? I mean, with M, we kind of say, OK, we'll start with 1 and then do something. And we know that 1 exists by kind of general things. But M was some module that we didn't know anything about. Here, F is a much more concrete module. It's the field. Okay? If you think back, you actually did this already. Maybe it doesn't look familiar to you if I write it like this, but if you remember that the field is the same thing as the polynomial ring modulo the maximal ideal if I take the polynomial ring and I mod out all the variables, then what I get is the constants. So I get my field. And we actually know how to resolve this. This was one of your homework problems. So let me just review the solution to that homework problem. So the way we did that was like this. This is, we gave this guy a name. This is the Koszul complex. Okay. And it looks like this. It looks like this, and then here we had this, what I wrote in blue, but I'm now just going to write F. Okay. So this is the way that we found a free resolution of the field, and it is a minimal free resolution. Now, so far, I'm only telling you some information, but I'm not telling you all the information. I should tell you what the maps are. And maybe I want to do it in two ways. First, I'll just remind you how it is in an example, and then we'll write in general what it is. So So for example, for n equals 3, we did this very explicitly, and it looked like this. The only thing is I'm going to write it in this notation now. So these are the maps, and the gradings work like this. This guy has grading 1. Then these 3 guys are graded by, are shifted by x, y, and z, which we put back over here. Then these guys, remember, were graded by y, z, x, z, and x, y. That over here. And this last guy was graded by, was shifted by x, y, z. Now you see that just by giving you this picture, you can recover the old maps that we had. The old maps had letters, right? For example, this was x minus y, z. But you can recover that because if this guy is in degree y, z, and this guy is in degree x, y, z, then this one really you should imagine that it's being multiplied by an x. And this guy by a y, this guy by a z. So this is the monomial matrix version of this. We talked about it quite a bit. Okay. Now, I told you that if you look at these matrices, these are exactly the matrices we get from homology. Okay. These are exactly the boundary matrices. Because, for example, the boundary of x, y, z is yz minus xz plus xy. The boundary of yz is y minus z. Boundary of xz is x minus z, etc. And so these are exactly going to be the maps of the Koszul complex. So now I'm going to write that with like this. So well, I think instead of I kind of wrote this in more notation in the notes. If you prefer lots of notation, then you can see it there. But I think that the way to think about it is that the matrices between these guys are really just the homology matrices. So there's one thing that I'm realizing, which is that I should reverse this. Of course, it doesn't really matter, right? Because n choose 0 is n choose n. N choose 1 is n choose n minus 1. N choose n is n choose 0. But the point is that here I want my sets of size n minus 1. And my boundary takes things of size n into things of size n minus 1. So, I'm sorry?
N choose 0, what's that next one then?
This? Yeah, sorry. Thank you. That's right. Okay. So delta I is just the usual homology boundary map. Now, like I said, the point is that if you forget about the blue stuff, then you could really just think of this as a homology computation. And the matrices are the same. And so this thing right here, let me say more concretely, just like we said last time, this is a big chain complex, but I can now look at the things that live only in degree B. Okay? And let's see what we get there. And again, I think the best way to see that is with an example. What do we get when we look at degree B equals, I don't know, 1, 3, 0. Okay. Just to read all of this stuff. I guess to make our life a little bit easier, let me just remind you that this guy is shifted by 1, 1, 1. These guys are shifted by 0, 1, 1, 1, 0, 1, 1, 1, 0. These are by 1, 0, 0, 0, 1, 0, 1. So these are the degree shifts. Okay. So now I'm going to say the following. I'm going to say, what are the things that I have in degree 1, 3, 0? For example, here, what elements have degree 1, 3, 0? So this is COSUL, and now I'm considering only the degree 1, 3, 0 part. So here I just get 0. Here, what things have degree 1, 3, 0? Well, you see, nothing has degree 1, 3, 0 because everything gets shifted up by 1, 1, 1. And you couldn't have had anything of negative degree, so that means that nothing here has degree 1, 3, 0. Now, what are the things that have degree 1, 3, 0 in this R3? Well, in the top coordinate, nobody has degree 1, 3, 0. Here, nobody has degree 1, 3, 0. And here, there are things that have degree 1, 3, 0. What has degree 1, 3, 0? Y squared, right? So it has to be the vector 0, 0, y squared. What else has degree 1, 3, 0? 2y squared or 5y squared, but that's it, right? It's just the multiples of y squared. So that means that what we have here is just a copy of the field. Right? Just you choose your number and you multiply by y squared. So this is just a copy of the field, which comes from this guy. Okay. What things have degree 1, 3, 0 here? Here we have things. Here, I guess y cubed has degree 1, 3, 0. And it's multiple, so that gives me a copy of f. Here there are things that have degree 1, 3, 0, which are x, y squared and its multiples. So I get 2 copies of the field. And here nothing has degree 1, 3, 0. Okay. By the way, there are degree shifts here. So this corresponds to the degree shift 1, 1, 0. And here we had the one of 1, 0, 0 and the one of 0, 1, 0. And finally, we go over here. What things have degree 1, 3, 0? Well, only x, y cubed and its multiples. So we get a copy of the field in shift 0, 0, 0. And here, what has degree 1, 3, 0? Nothing, right? Because everything is a constant, so everything has degree 0 here. So what we get is this. Okay. Now, what are the matrices then? Well, here we're only mapping from here to here, okay? And so our transition matrix is basically what happens when we restrict to 1, 1, 0 is which column? It's this column. And these are the top 2 columns. And so my transition matrix is this one right here. And here, we're looking at this column, and this row. So the transition matrix looks like this. And if you look at this, this is literally and exactly the chain complex in homology of something. Of what? Well, basically what you do is that you tell me what are the faces of this guy. X, Y is a face, X is a face, Y is a face, and the empty set is a face. And this is exactly the chain complex that we use to compute the homology of a simplicial complex given by what faces? The face xy, the face x, the face y, and the empty face. Because remember that what we're supposed to do in this case is put the zero-dimensional faces, so we put f to the zero-dimensional faces, then f to the one-dimensional faces, then f to the two-dimensional faces, and then take the boundary maps. So this is just a homology computation in degree 130. So what we get here is the chain complex to compute the homology of what? Well, if you look at this, basically the things that got to appear were basically, because 130 involves the first two variables, then everything involving the first two variables was fine. But anything that involved the z variable we had to throw out. And it's going to be the same thing here. B is some vector. It has some things that are 0, some things that are not 0. And what we're going to get is exactly the chain complex to compute the homology of the simplex whose vertices are the support of B. So this is the non-zero coordinates, basically. So this is something that I kind of said loosely before, but now I'm really saying it very concretely. This is our free resolution for the field, okay? And I said before that it kind of looks like a homology computation. What is it that I mean exactly by that? What I mean is that this is a big thing that has lots of graded pieces, right? And if I look at each graded piece, then in each graded piece, this restricts to something that has basically more or less the same maps, but now instead of copies of the ring, we have copies of the field, which is what we have in homology. Okay? And so in each graded piece of degree B, I am really computing an honest homology. Okay? Now, you see that this is an exact complex, right? Because it's a free resolution, it's exact everywhere. That means that when I restrict to degree B, it should still be exact. Okay? So maybe we should get a little bit worried because we're supposed to be computing homologies, and yet we're getting an exact sequence where there is no homology. Okay? But the reason we don't have to worry is that if we see the way that this guy looks, we know that this guy has no homology. Okay? In this concrete example, this was exact, so this was exact. Okay? And it's no surprise that this is exact because this is the homology of this complex, which has no homology. And well, this is true for this edge, but it's actually true for any simplex. This is something that we proved, actually. So that's why it's exact, since the simplex has no homology. So what's my plan after this then? Remember what we're trying to do is we're trying to compute MF by taking a free resolution of F and tensoring it by M. So I wanted to talk very carefully about the free resolution of F. It looks like this. We understand it very well. Okay? And now what I need to do is take this free resolution and tensor it by M, by I. And when I tensor it by I, and I look at the component B, then I'm supposed to get some homology. And now maybe at least it's not so surprising because in degree B, this is a homology computation. Now the thing is that something needs to happen so that instead of computing the homology of a simplex, we're computing the homology of this upper Koszul complex. So we'll see where that guy comes from next time. So that's how we're going to conclude this proof. We'll continue next time. Today's the... Is yours? Yeah, right.
We were wondering, when you say it has, the simplex has no homology, do you mean it has like trivial homology?
Yeah. So it's 0 in every dimension.
And then they just don't exist. Sometimes we find that there's no map, so we couldn't compute a homology proof at all.
Yeah, so right, so basically